Hello, welcome to MacMod Analytical's hosted webinar called The Introduction to GC Method Development. I'm Jeff Faden, your moderator. I'm the president and CEO of MacMod Analytical. MacMod was established in 1986 for sole focus to bring innovative chromatography solutions to the North American marketplace. Just a little bit of housekeeping. If you have any questions during the presentation, please type them into the chat window. You'll find it on your little GoToWebinar widget. Include your name and company if you would like, and we will do our best to answer as many questions in the allotted time slot as possible. Today's talk will be given by Kirsty Ford. She's the Senior Chromatography Technical Specialist at Avantor Sciences. She's part of the technical team supporting colleagues, distributors, and customers worldwide on a range of chromatographic products, including GC and HPLC columns. With experience as remote support engineer with Agilent Technologies, focusing on GC and GCMS, they bring a wealth of knowledge in chromatography troubleshooting and product insight. Thank you for joining us today, Kirsty. I'm going to turn it over to you.
Hi, thanks very much for having me. And yeah, I'm really excited to do this presentation today and to look forward to your questions at the end as well. So we can get started. So just let me know if you can see the slide changing.
Not yet.
Okay. That just seems it's going a bit slow. One moment.
There you go.
So 1 second. So it should be on the screen now. Just let me know if you can see it. It just moved. Okay, it looks like it's okay for me. So it should be on the first Avantor screen. Can you just check that's on there, Jeff, for me?
Yep, that's perfect. Ready to go.
Perfect. Perfect. There you go. Technology, always testing us. So today we're going to be talking about basically introducing you to different approaches to method development and some guidelines that are going to help you get the resolution that you need out of your applications. So first we're going to look at establishing objectives, tools, and selectivity. Then we're going to look at optimization of the GC parameters and what that's working towards. Then we're going to have a look at standard GC method development with split and splitless injections. Then we're going to go into fast GC and how we can transfer a method from standard to fast GC. So where do we start? Sometimes getting started with the method development is sometimes the most difficult step to take. But if you take a step back and then just try and organize what you want to achieve and what you have to achieve it. So have a look at what are your analytes of interest in your sample. What's the aim of your analysis? Is there an application that you're working on specifically? What's the GC configuration that you have? Then what GC column phase do you require? And then what is actually in your sample mixture? So when we think of the analytes of interest, what are they? Because we don't necessarily need to be interested in every single analyte that comes out in the chromatogram. Are the analytes of interest, are they actually suitable to be ran for GC? And then what are the physiochemical properties that influence the changes and adjustments that we need to make to the parameters? So HPLC is very popular just because it's a little bit more flexible with the type of compounds and samples that we can analyze. But GC is just very specific for volatiles, semi-volatiles, and permanent gases. The boiling points tend to be low, below 400 degrees centigrade. We need the analytes to be easily vaporized and volatile, low molecular weights, stable at high temperatures, high vapor pressure, and they tend to be organic compounds. With HPLC, we've got a wider range of compounds that we can analyze, but these tend to be a little bit more unstable when you get to the higher temperatures. They have a wider molecular weight range that we can have a look at. They may contain salts or carry a charge. And again, organic, but also inorganic compounds. So when we think of essential oils, which is going to be more suitable, GC or HPLC? So when we look at essential oils, they've got low boiling points, approximately 100 to 200 degrees, easily vaporized, low molecular weight, stable within a certain range of temperatures. Then we've got high vapor pressure, organic compounds, and they're soluble in a liquid phase. So they work really well for GC, but we can still analyze them for HPLC. So this is a good way to just double check what you're actually analyzing. And yes, you might be able to do it on HPLC, but GC is also there because it's a very specific analytical technique and we need to take advantage of it. With the physiochemical properties, these can influence the method direction. The polarity can influence the column phase selection. The boiling point of your analytes and compounds of interest can impact the temperatures that you're using on the inlet, i.e. the injector or the oven. They may have similar or different boiling points, and this can influence phase selection, and we'll go into that in more detail later. Then with structural isomers, if you want to separate these, you may want a more polar column, mid to high polarity. Again, we'll discuss this more later. If you've got a non-labile or labile compound, labile compounds need different conditions that are softer and have lower initial temperatures. The sample matrix, is it clean or dirty? This can influence the column dimensions, liner, consumable choices, and then the sample prep process as well. So aim of the analysis and the application. So what are you actually trying to achieve? Are there any specific application notes that you can use, or maybe you're already using them? And are there any application specific columns available? So when we look at the aim of the analysis, we need to consider what information do we actually need from the results? And then what do we have at hand to help us develop the method? So is it a new method or is it an established method? When it's new, it's a bit more of a blank canvas and it's a bit more flexible. But if it's an established method and maybe you need to follow some similar method trends within your lab, this is something to consider. Is the analysis simple or complex? Because if you're looking at just a few compounds, then it may be a little bit more straightforward than a more complex sample. Do all the analytes actually need to be detected and separated, or are there particular ones of interest compared to the others? Do you need high level or low level resolution? Because not every sample is going to require, very high level resolution. Then are there any application notes that are relevant to you? And then what level of sensitivity is required? Because when we look at the example on screen now, this PCB mixture, we may want to see all of these peaks, but it may not be necessary to see them all in a great resolution. Then compare it to this figure where the hydrocarbons, they're very well resolved. There's only 4 analytes in this chromatogram, but we might need to see them with great resolution. So that's quite a difference from the PCB mixture. So these are the kinds of things we need to think about, because it'll help you make decisions on the products that you're using and checking your GC configuration actually works with what you're trying to achieve. There are a number of resources out there, along with USP and then other monograph resources. We have a GC phase document and a cross-reference document to help with offering columns that may be suitable for your application, or cross-references for columns that you're currently using. We have some application notes, and that resource is building every month. We're adding more and more technical notes and application notes for GC. And then also, if you're having a look at the specific USP phase that has to be used for certain methods, you can also check that as well. So for your GC configuration, what is it? And what inlet, what detector, samplers do you actually have? And is this suitable for what you're trying to achieve? One of the most important configuration aspects in GC is the choice of carrier gas. Nitrogen is one of the original gases that was used with packed columns. It's the second most viscous and has low diffusivity. Excellent resolution, but it's really slow. So unfortunately, it just gives really long retention times. Helium is the most popular. It's the most viscous of all three gases, but it has quite a high diffusivity, higher than nitrogen. Then the most efficient carrier gas, which everyone's being recommended to change over to, is hydrogen. This is the least viscous. It's got the highest diffusivity of all the gases. So these sorts of qualities influence how fast the gas will travel and the pressure. So carrier gas linear velocity is the speed the gas will travel. So why does this matter and how can we harness this in GC? So to get theoretical, the HETP, which is the height equivalent to a theoretical plate, it's a way to measure column efficiency. The lower the value, the better. And when you look at the diagram, the Van Diepter equation, you can see with the blue line with nitrogen, it goes from 10 to 15 centimeters per second, where it's got the lowest value, and then it starts to increase. So this is where we start to lose the column efficiency when that HETP value starts to increase. With hydrogen, we've got a little bit more range between maybe 15 to 30, maybe 35 centimeters per second, where when we start to increase the speed of this gas, then we start to lose the column efficiency. But hydrogen has a lot more leeway and we can go much faster with it. So then the faster we can get the faster the gas can travel, then the shorter the retention time. But if we're going too fast and then we're losing the column efficiency, we're not going to get the resolution that we want. And it's the same if we're going too slow, too low in the velocity, then we're not going to get the resolution here either. So we're going to get peak broadening, and then we're also going to get slow retention times if we're going really low in the carrier gas linear velocity. So this is why the linear velocity is important. We need to find the right balance and get that optimum level. And hydrogen gives us a wider range and a faster velocity to play with. The GC configuration, what have you actually got on the GC? Sometimes we're not too sure because, especially with the injector or the inlet, I'm going to use inlet to refer to the injector, just because I know everyone likes to use different lingo with it, but I'll use inlet just for the sake of this presentation. It can be packed away, and then we might have methods that are already set up that maybe we're not playing with or changing. So we're not too sure what type of inlet that we've got, but it's really helpful if you understand what you can do with that inlet, because then you can harness that in your method. Same goes for the detector. We tend to have more information on the detector and what we can do with it, especially if we have an FID. That's a universal detector, and then an MS. But some of these detectors are really, really specific, and we can't necessarily analyze everything with these detectors. So it's just good to have that awareness of what you have, especially if you have things like headspace, thermal desorbers. We're not going to be talking about auto samplers or any other sampling techniques today, just because we haven't got the time, but it's something that we'll be looking at in future. So then when we have a quick look at the inlet type, we can actually see the differences between a splitless inlet, which is the most common inlet that's usually set up with a GC, Coulomb column, and then a PTV. You may hear the more common version of a PTV is an MMI, which is a combination of a splitless inlet and a PTV inlet. With the splitless, we can do hot injections for non-labile samples. But then when you look at the Coulomb column, it does have a wide boiling point range, but it's for chemically and thermally labile samples. So immediately there's a difference in what you can actually do with that inlet. Then with the PTV, this is cold injections and then rapid heating. And with each of the inlets, it has different capacities for its concentration. Again, splitless, it's a general inlet, so it can go high concentration and then it can do low concentrations as well. Coulomb column is restricted for low concentrations, and then the PTV has a bit more flexibility for high to low concentrations as well. There's a number of different modes. I won't go through them all today, but I'm just going to mention split mode and then splitless mode for the splitless inlet. With the Coulomb column inlet, we can only do cold splitless, and there's no liner. So again, understanding that is where you can see what you can actually do with that inlet compared to, say, a splitless. Then with PTV, we have split modes, splitless, and there's a few other different types of injection modes available. With the liner type, very different for each of the injection modes. With the split injections, there's a lot of flow going through the inlet and through the liner. So these tend to be straight liners. You can use them with or without quartz wool. You can have more specialized liners, a straight cyclo liner. Then with the splitless injection, this is different. These have goosenecks. They might have a double gooseneck with or without quartz wool, and this helps focus in the sample. So if you put, say, a splitless liner into a split mode injection, then you may see issues with your chromatography because that liner is just not suitable for high flows. Then when you look at PTV, we have baffled or dimpled liners. So these have these geometries to help with the movement and the mixture of the sample whilst it's going into that cold injection environment and then rapidly heating. So straight away you can see that some of the decisions, the products that you want to use are influenced just by the type of inlet that you've got. And then you've also just got to make sure that it's compatible with the type of sampler that you're using, whether you're using maybe a headspace sampler, etc. And then also make sure you've got enough vapor volume within the liner to accommodate for the vapor volume of your solvent and sample. With the column phase, what phase is going to retain and separate the analytes to fit the results that you need, and what dimensions are going to be most suitable. So the most common phase chemistries, we'll go through them now. We've got non-polar on the left, dimethyl polysiloxane, 100%. Then on the right, we've got polar high polarity phases, polyethylene glycol, or wax columns. And the stationary phase is essentially a liquid coating of polysiloxanes or polyethylene glycol with substituent groups. And then as we add these substituent groups, it increases the polarity. And then this gives more separation mechanisms, the more polar the phase becomes. You can see this would usually maybe be from our selection of columns, a high 5. So this is a low polarity column with 5% phenol, replacing some of the methyl groups. Then we've got cyanopropyl phenyl. You can see the percentage changing. So this is just a few variations of the types of phases that you can use. Here's just a summary of some of the phases that we do. And you can see we've got the high ones on the lower end of the polarity. And on this non-polar end of the spectrum, basically the boiling point influences the elution order. And then the more and more polar the phase becomes with these replaced methyl groups, then the phase interaction influences the elution order because there's more mechanisms of separation that the analytes interact with. The main thing to remember if you're looking at a phase and you're not sure where to start is that like attracts like. So the strongest interactions are going to occur when the stationary phase and the analytes in your sample have similar polarities. It might not be where you end up in your column phase selection, but this is a really good place to start. So then when we have a look at column selection, a really important aspect is the resolution, because we don't want to invest in a phase and then it turns out that the resolution isn't that great and we could have made a better decision initially. So there's 3 strategies to achieve decent separation and ways to improve the resolution. And these are efficiency, selectivity, retention factor. And as we all know, with resolution, ideally we want a value of 1.50 and above, and this will indicate this baseline separation of the peaks. Any value less than that, there's going to be some form of coelution or issue with the resolution. So to improve it, we can work on the efficiency. So this is the number of theoretical plates in the column, relating to the dispersion of the analytes in the column, and then achieving narrow peak widths. And we can adjust the carrier gas, the length, and the column ID to improve this. Adjustment of the carrier gas flow can be in the flow rate or even using a more efficient gas. We talked about the column efficiency earlier on the earlier slide and the velocities that you can work with. So this is an important point here. Using a smaller ID helps to increase the number of theoretical plates, but you lose out on less capacity because there's less space inside the column to inject your sample, and then there's higher pressures. So sometimes we can't just jump to a smaller column ID, it depends on your setup. Then we can also increase the length of the column, because the longer the column is, we can increase the resolution, but this should be a last resort, because even doubling the length of the column doesn't double the resolution, it only increases it by 40%, and then your analysis will be twice as long. Then when we look to retention factor on the right, this is where the ratio of the time that's spent by the analytes in the stationary phase compared to the mobile phase. Maybe this is not optimal and we need to work on this to improve it. Because we want an appropriate reaction of the analyte so it's interacting enough so we can get good separation. And if there's not enough time for the analytes to interact with the stationary phase, we get poor separation. Then if it's spending way too much time in the stationary phase, then we get peak broadening. So we need to manage this by using temperature of the oven, the film thickness, and the column ID. So we can adjust these options that we can choose for our column. Because when we have a retention factor between 2 and 10, these are the values that we're looking for, and then we can start to improve the retention based on these values. An unretained compound has a retention factor of 0, and then less than 2, there may be a little bit of separation, but you might just see a hump or just not great and not a peak really at all that you can use. So then when we've got a value between 2 and 5, these are the early eluters. So for better resolution, we can increase the film thickness, decrease the temperature, or if it's, sorry, this is because it's eluting too fast. So we need to make sure that we're creating more retention. So this is why we have a thicker film thickness and decrease the temperature. If we've got late eluters, then these tend to have a retention factor above 5. And these peaks may be showing peak broadening. So for better resolution, we maybe need a thinner film thickness and then increasing the temperature. So this will help the analytes elute faster. But one thing to mention that as the temperature increases, the retention factor is going to decrease. So there are caveats when we're changing these parameters. And then when we get to the most important point, the most important strategy is the selectivity. This is the most influential on the resolution. So you need to choose a phase that's selective enough for your compounds. We don't want to go for a super expensive, really expensive polar column if actually you're not going to benefit from the separations that it will give you. So the selectivity relates to the stationary phase and how the target compounds and analytes interact through the separation mechanisms that more selective columns can offer. We'll go into the mechanisms in the next few slides. So when we're choosing an appropriate column phase that's selective for what you're looking at, you can check this through retention indices. You can have a look at application notes and have a look at the retention between 2 compounds of interest, 2 peaks of interest. And then the selectivity is the distance between these 2 retained compounds. So this is a bit of a difficult one if you have already got the column phase, because you may have to run some experiments and actually have a look. You may have some practical data that you can use, but if you've not purchased the column and you're not sure and you want to look at the selectivity, this is where researching application notes, looking at retention indexes is really, really helpful, because the evidence is there and there's lots of information out there to help you choose the most appropriate column. So then when we look at the separation mechanisms, for non-polar, you can see that they're strong dispersive, no dipole, no hydrogen bonding interactions. The types of compounds that can be analysed here are carbon and hydrogen atoms, carbon to carbon bonds. Some of the example groups are alkanes, but these all elute in boiling point order. And if you inject a sample and it has a group of compounds from the same compound group, they will elute in boiling point order. Similar, when you get to the low polarity phases, there's low polarity interactions that are strong dispersive, no dipole, but have weak hydrogen bonding. So again, those replaced methyl groups. slightly different interaction mechanisms. So you're going to get a slightly different separation compared to a 100% dimethyl polysiloxane that hasn't had any of the methyls replaced or substituted. Then, when we get to mid to high polarity phases, the interactions and the mechanisms are strong dispersive, strong dipole for cyanopropyl, moderate dipole for trifluoropropyl, then moderate hydrogen bonding. You can see the compound types that tend to work well with these phases slightly change. These are just a few, it's not all of them. And then when you compare that to high polarity and polar columns and their interaction mechanisms, we have slightly weaker hydrogen bonding, but we still have strong dispersive and then moderate dipole. And again, some of the compound types, a bit more selective, say for alcohols, carboxylic acids, diols, esters and ethers, etc. But it doesn't mean that you can't inject other samples on a different phase. It just means that the higher the polarity, there is slightly more selectivity for particular compounds and analytes. An example here is where we have a nonpolar column. It's the high 1 column, and we've got 4 analytes, and we can see they've eluted in boiling point order. So the highest boiling point, the larger compounds have the higher retention. Then this compared to a polar column, a higher polarity column. They've eluted in the order depending on the polarity, but also the interactions that they've had with the phase, because there are different mechanisms of separation when we increase the polarity of the phase. So the elution order is not in boiling point order. And then when we look at the dimensions, this goes into a little bit more detail just of the benefits of different dimensions. So say if you're looking at a column with a mid-length, so 20 to 30 meters, this can offer around medium resolution. It suits a broad range of analytes, moderate retention times, medium cost, tends to be a general length used. And you can use it for medium complexity samples, and you can also use this with GCMS. And then just to go back, so then if you look at the shorter column, you can see that lower resolution when it's on its own and you just shorten the column, but it has a shorter retention time, shorter cost, and it's good for things like screening, high boilers, fast GC, GCMS. And then on the length as it increases, so 60 to 100 meters, you can see at the bottom, it says very complex samples, low boilers. So you can just slightly see how some of the applications can even fall into things like the length of the column. Then when we look at the column ID, the internal diameter, if we look at the larger bore, so 0.4 to 0.53 millimeter ID, these are good for high flows. So then if you're using headspace, if you've got split flows, a lot of flow going down that column, high capacity samples, and then you may have longer retention times slightly just because there's more space inside the column. And then when you look at the medium, more common IDs, so 0.25 to 0.32, again, more medium sample capacity, moderate flows. And then as you get smaller and smaller, a little bit more restrictions, lower capacity, but then these are more beneficial because then you have shorter retention time and you can use these with fast GC and GCMS. Film thicknesses, we've talked about this quite a bit today. So if you have thinner film thicknesses, there's a decreased retention, shorter retention time, but there's also lower capacity of the sample that you can introduce onto the column. But as a benefit, less column bleed. You can use higher temperatures compared to the thick, so the 1 to 10 micron. May have higher capacity and increased retention, but you have to use lower temperatures in the oven because a lot of that phase is going to bleed off. And you can see it's more suitable for volatiles and low molecular weight compounds. So even the dimensions give you a really good direction as to what's going to work with your application and your method. Sample mixture. So ensuring that there's a decent sample prep protocol and that works for your analysis is really essential. Understanding what's actually in your mixture, even if it's unknowns, just understanding some of the compound groups that are going to be in there, and then the type of diluent that you want to use. Again, we're not going to go too much into sample prep or sampling introduction methods today, but just a quick mention that for lower polarity samples and columns, you do want to try and work with lower polarity solvents if you can. And then same for polar analytes and polar columns. So for example, methanol. We just want to avoid extremes. So say using methanol with a non-polar column, 100% dimethyl polysiloxane, just because this may have negative effects on the phase. You can also use a intermediate polarity solvent if you're maybe using a mid polarity column, or if you've got a mixture of polarities in there. And just the other considerations of the sampler type that you're using, detectors, you just need to double check that everything's compatible. And then if you're doing different injection techniques, check the solvent has the suitable boiling point. It tends to need to be lower than a sample mixture for most basic injection techniques. So when we run through some of the objectives, we're all ready to go, we understand what we're working with, then we can have a look at actually developing the method when it comes to the parameters. So I won't spend too much time on this, but with the first approach, if you've got an application note and there's quite a lot of resources to help you get started, then you can start to set up your method based on these parameters. Make sure you've got the correct test mixture, because you don't want to set up your method and then have the wrong test mixture and then seeing all these different peaks that you weren't expecting. So just double check that if you're using an application note, that you try and use it as closely matched to the application that works for your GC and the configuration. Adjust as needed. If you've got different detectors, just double check that what you're going to inject is going to be suitable. When you run your injection, do your first scout run, have a look at what you're seeing, and if you're seeing any major issues, start to change a few parameters one by one, and then do another run, and then just keep doing this. And then if you're still seeing serious issues, then you can go back and just check if there's any issues with the GC. Same goes again when you are starting from scratch. Maybe you're just using a default method from the software and you're not really sure of where you should be starting. So set up the method, adjust the parameters as needed, make sure you're not going to be overloading the column, so just have a look at the column capacity, run an injection, and again, change parameters one by one, because if you do it all at once, then you're going to lose track of which parameter you changed when. So just try and at least document it if you're going to change a few at the same time. So we're just going to do our first injection. So we're going to do a split injection. We're using some standard column dimensions, so 0.32 millimeter ID, 25 meter length column. We haven't got the film thickness defined here. So again, when I mentioned the capacity of the column, just make sure you're not injecting too much. You can check these values online just to double check what's the capacity of your column if you're not too sure. We've just got some standard settings. These are usually default in a lot of GC software. We tend to want to develop methods in constant flow unless the application says otherwise. It's just a little bit difficult to keep control of the flow and the velocity if it's in constant pressure. We've got a split ratio of 50:1. So if we've got 1 mil a minute going down the column, then this is 50 mil a minute going out the split flow. Standard initial temperature to start with, oven ramp rate 10 degrees per minute. So let's run an injection. So this is a split injection for high concentration samples. The arrows are going into the column, out the purge, and then out the split vent. The split vent is open through the whole injection and after. The sample is introduced into the inlet and liner, vaporized, then the majority of the sample goes down and transferred onto the column. Then the rest is vented out the split line. So this is just an approach to what you can adjust initially. Obviously, you can do it in any order that works for you, but this is just a few steps of guidance just to help. So what did you actually see on the first run? Overload is really common. So the first thing you can adjust is the split. If you've got 1 to 50 to start, or maybe 1 to 100, whichever one you're starting on, you can just change it in a few increments, just to make sure you've got enough sample being transferred onto the column without overloading it. If you're still seeing issues, even if you've got a really high split flow, then just double check and make sure that you may need to reduce your injection volume or dilute the sample in some way. And then if it's really not working, then start to look at the sample prep process and adjust the concentration. But if you're still not getting anywhere with this, then maybe it's just going back and assessing what's wrong and why the column is struggling to take on the sample. If you're getting a low response, again, you may need to increase the split ratio because you may be losing the majority of the sample out the split vent. And then the same goes again, increase the volume if you can, if it doesn't exceed vapor volume expansion inside the inlet. And then increase the concentration as a final resort. Again, if you're having issues, then just going back and double checking what's wrong, just in case there's something going on wrong in the sample prep process or the sample introduction stage. Peak degradation. If you see this, this tends to be something to do with the inlet temperature. Usually this is left at 250 degrees, but if it's too high, sometimes you can see degradation. So this is something where you can reduce it or increase it as needed, but we don't tend to adjust this too much, but you can change it if you need to. Retention time issues, obviously this is a big area. So this is just from the method development, the first injection perspective. Just adjust the flow, make sure it's consistent, make sure you've got it in constant flow or constant velocity mode. And then just adjust the flow rate or the velocity by some steps and just see if this makes a difference. So then when we look at the oven, how we can change this if we're still seeing issues, poor resolution. So maybe we just need to optimize the oven ramp rate. So you can try this in a few different steps. You can run some calculations for the T0 time, so 10 degrees per the T0 time. This is a bit more theory that I won't go into right now, but it's something that you can look at. Retention time issues. Again, increasing the temperature can speed up the retention time, but just have a look and just make sure that it is consistent and just check your oven ramp rate just in case you need to slow it down or speed it up. With the final temperature, double check the elution temperature of your final analyte, check it's actually eluting, and then just try and calculate that final temperature and add 20 degrees, and then just see if any of this is going to help with retention time issues. If not, then maybe you need to have a look at in where that late eluting peak is going and why is it taking so long to come out. You can have a look at your initial oven temperature. Is it too low? Is it too high? So have a look at the eluting temperature of the first peak, and then have a look at that temperature and try starting around about there. Not all peaks eluting, so they're obviously being lost somewhere, or maybe this is out the split vent. So this is more issues maybe with the sample introduction. But if you're losing them at the end of the run, maybe adjust the hold time because you might be losing them here. Co-elutions, you can add a hold over mid-eluters if needed. But a lot of the time, this is more of a bigger problem if it's something to do with a column that maybe isn't very selective for the analytes of interest, but you can adjust the method to improve co-elutions. You can also optimize the oven ramp rate as well. So try increasing the temperature, increasing the temperature of the oven ramp rate so it speeds up quicker, or you could maybe make it slower. So maybe go 10 degrees per minute, go to 20, go to 30, and then try and work out which is the optimal. Splitless injections, they are a little more complicated. So we have a splitless hold time when we're injecting the sample. So this is the time when the split vent is closed and all of the samples being transferred onto the column. And then after a certain amount of time, so you've got up to 2 minutes, standard maybe 1 minute that's already in the default software method. Then the split vent opens and then there's a purge flow. Usually it's around about 50 ml per minute. And this clears out any residual inside the inlet. And this is different to split injections because the initial temperature is below the boiling point of the solvent because we want to introduce a sample with like a cold film onto the column, and then the sample is then recondensed onto the column and then heated up. So it's a completely different approach to split injections, which is why we need this hold time at the beginning to make sure all the samples transferred. This also impacts the oven temperature because we have the oven temperature fairly low at the beginning just to accommodate for this hold time. So let's run an injection. So again, you can see that the split vent, the purple vent, is closed. So this is for low concentration samples where we need pretty much all of the sample to be injected onto the column. And then when the split vent opens, this is an optimized time after the sample's been transferred efficiently. And this is why it's a bit more of a tedious injection, just because we need to not have that hold time too short or too long. So then when we're optimizing this method, what do we see after the first run? It's going to be a little bit more challenging, but some of the same processes are the same. So we're seeing overload again. Rather than thinking about the split ratio and how much we're sending out the split vent, we need to think about, is the sample volume too much? Is the concentration too much? And maybe we need to reduce them. Low response, maybe we're losing some of the sample because that hold time isn't long enough. So you can adjust this. You can change it in increments if you want to, but you can also calculate 1.5 to 2 times carrier gas sweep in mil per minute. And then you can adjust it and just see what time that takes you to. Injection volume, again, you can adjust it and increase it if you need to, and then the concentration. Same goes again for the peak degradation. This is again a little bit more tedious with it being a splitless injection, but this is more of a last resort, adjusting this inlet temperature. Again, with retention time issues, having a look at the flow rates and make sure these are appropriate and adjusting as needed. Carryover, this may be where the flow after the hold time is not enough. Maybe we need to increase the flow rate just so we can sweep that column and any residual left over to rule out any carryover. Same goes again with oven parameters that you can change, but it's a little bit different with splitless because we have that hold time. So we have an initial hold time that we didn't have with split injections. So we need to make sure this is matching the inlet hold time, that time it's injecting the sample and transferring it. Because if we start increasing the temperature too quickly, then we're going to lose the benefit of a splitless injection. But if you're seeing peak widening and resolution issues, again, have a look at that initial temperature, make sure it's low enough. Reassess to make sure that the solvent's suitable for a splitless injection. And then, again, double check the oven ramp rate and adjust this as needed. Same goes again for the retention time issues that we mentioned before. If not all the peaks are eluting, again, double check that you're matching the initial hold time of the injection. And then the final hold time, make sure you're not losing any of the late eluters at the end of the run and giving plenty of time for them to elute. Co-elutions again, you can add some temperature holds, adjusting the ramp rate, checking the final temperature of the last eluting peak. So we've gone through a few ways you can adjust the method as you're developing it. So we want to make sure we've transferred enough sample onto the column for detection. We want to see all the peaks elute, and if we're not, what can we adjust to get those peaks back? Reduce the retention time, because we want it to be good resolution, decent separation, but also not taking too long. We want to see the good peak shape, again, the resolution. There's lots of things we can adjust to improve that. We want to see a good response to enable concentration calibration. And then once we've got this method established, then we can start to move on to ensuring it's reproducible and then moving it on for validation. So with FastGC, this allows you to run methods from a standard column dimension where you can run it in smaller dimensions and reduce the retention time. So you can apply it to medium to high complexity mixtures. Great for screening analysis. And then you can maintain similar retention and elution order as well, which is really beneficial. So we've got this data. So we've got a standard GC method at the top. It was a very short run anyway, with being around 11 minutes. We would have liked it to have been a lot longer, but 11 minutes is still, we can improve that. And we did improve it to 3.2 minutes. And you can see the difference, and we'll go through them in the dimensions. So we've gone from a 0.25 ID, 0.25 micron film thickness and 30-meter length low polarity column. And we've gone all the way down to these smaller dimensions. And there's been some adjustments to the method to accommodate for this smaller column dimension. So just a reminder what we need for fast GC. We need to reduce the retention time. So we have shorter length columns, higher temperature ramps, usually more than 15 degrees per minute, higher gas linear velocity. We've mentioned that a lot today, just makes the column more efficient and be able to accommodate for the shorter and smaller dimensions. Then for these retention times, we need the configuration of the GC to keep up. So we need to use the carrier gas of hydrogen because it travels much faster. We need the smaller ID, so then we can still maintain the resolution because we have increased number of plates, as we mentioned before. Then we have the thinner film thickness because we've got these higher temperatures and higher flows. We also need fast acquisition rates because the data is going to be coming out fast, so we need a frequency of at least 50 Hertz. Then we need fast injections and split mode injections, so manual injections are not going to be suitable. So let's do the quick walkthrough of the transfer from standard to fast GC. If you want to maintain the retention and the elution order, then you use the phase ratio and you basically look for a similar value. For example, if we look at the green, we've got this 0.25 film thickness and then a 0.25 millimeter ID. It's got a value of 250. These green values tend to be below 400, so this is high molecular weight analytes. And you can move down to smaller dimensions and just look for a similar value between maybe 50 units, and you can maintain similar retention. So this is really important because you don't want to be changing dimensions and then completely changing the retention. You want the phase ratio of the ID and the film thickness to be as similar as possible. You'll get this information afterwards. It's just to show that you can calculate the phase ratio just to try and find a suitable smaller dimension, but with a similar phase ratio. So then when we had the standard run, you can see the peak IDs, and then so we've got a flow rate of 1.2 mil per minute, linear velocity of 35.7, split ratio 75:1, injection volume 1 microliter, and we've got 10 degrees per minute in the oven ramp. So this will all change. So first, we adjust the split ratio because we don't want to oversaturate the column. We need to reconfigure the column dimensions and the carrier gas in the software, especially if we're moving to hydrogen. And we just want to reduce everything down. So we want less sample going in there. We want a higher split flow. And again, use constant flow or constant velocity, not constant pressure. And then you can see the first adjustments, we've reduced the injection volume and the split ratio because the minimum is 1 to 100 to avoid saturating the column and to try and avoid excessive overload. So we run the injection. And then you can see the response has dropped, but that's normal because we're introducing less sample. And we can see the flow rate's already adjusted from 1.2, I think it was, down to 0.245, even though we've kept that linear velocity the same. But the software has calculated that it needs a lower flow rate to accommodate for these lower dimensions, these smaller dimensions. So let's see if we can improve it. So we've increased the split flow on here from 1 to 1 to 100 to 1 to 200. And you are going to see a drop in response still, just because there's less and less sample. But you just need to drop it to the appropriate amount. And then if you need to increase it again, that's fine. But as long as you can see the resolution of your peaks, then you can continue adjusting the method. So then we need to increase the carrier gas linear velocity so we can reduce the retention time. You can increase it in steps of 10 centimeters per second. Just remember that as the velocity goes up, the retention time will go down, but the column flow will increase and the split flow will increase. So just make sure you're having a look at the peak shapes. And if you start to see things like overload, then maybe you need a higher split ratio. If you start to see peak loss, then maybe the split ratio is too high and sending too much of the sample out of the column. Then we run another injection. And you can see that we have various linear velocities, and you can see that the flow is changing. So we go from 0.25 to start, then we go to 0.345 mil per minute as we get faster and faster with the velocity. And we can see that the retention time is reducing. So you can set up a few runs, adjust the velocity, and then see which one gives you enough of a retention time reduction without losing too much resolution on your peaks. Then the final stage, increasing the oven temperature amp, because this will even further reduce your retention time. If you get it too high, you're going to see peaks maybe too close together. So you can run some theoretical calculations to try and find the optimal oven ramp rate. So I won't go into this now, but you can have a look into this, and it's very helpful if you want to run some calculations and predictive oven ramp rates that you can try. So then we try increasing the oven ramp rate, and you can see it gets shorter and shorter, and this is really, really powerful. We're going from above 8 minutes all the way down to less than 3 minutes. Just to note as well, you don't necessarily have to do it in this order. You can't adjust the oven ramp rate first. But just to show you, this is a very powerful way of reducing the retention time, and none of the peaks are eluting too close together either. Then the final run, we've got the increase in linear velocity, and we've got 30 degrees per minute for the oven ramp. And you can see we've got less than 3.5 minutes. So when we compare them, you can see we've gone from above 11 minutes and we've gone down to 3.2 minutes. And really, we've not changed that many parameters. But as long as you're doing it step by step, you can monitor and check what's going wrong, go back, adjust, and you can try and find the optimal settings for fast GC method setup from standard GC. This is just a summary of what you need to do. So acquire the smaller dimensions, reduce the flows, dilute the sample, increase the linear carrier gas linear velocity, and then utilize the faster oven ramp rate. And this is what you need to eventually transfer your method to fast GC. So apologies if I've gotten over by a couple of minutes, but thank you very much for listening. And does anyone have any questions?
So thank you very much, Kirsty, for that wonderful presentation. We have a few minutes to answer questions from the audience. I want to remind everyone that you can type any questions into the chat window. Please include your name and company, and way we do not get all the questions, we can follow up with you after the webinar. So we received the first question. Do you have any suggestions for sticky analytes? We start with good precision, but after testing many samples, we start seeing issues.
Yeah, so this is a tough one with the sticky analytes. It will be dependent on the sample introduction type, and then also afterwards, if there's a process to kind of clear out the inlet and purge the column post-injection. But I think the best thing would be to do is just to assess the consumables that are being used, and then other ways of like the liner, syringes, things like that. If you're seeing issues, then have a look at ways to purge and clear out any residuals that may be causing issues post-injection, and just have a think about the sample introduction technique and if it's efficient enough, and is there a way to improve it? Can you run blanks in between these injections? Is there a better liner out there that may be a bit more suitable for you know, these tough matrices that you're working with? Yeah, so that would be my advice, just to kind of have a reassess of the sample introduction, the consumables, and then ways to help remove any residual that's left over post-injection.
Great. So we've had a lot of questions asking for the slides. So just for everyone's information, we will be sending the slides in a PDF format after the talk. A second question here around peak broadness. So for my compounds, peak broadness is a large issue with some compounds. How do we ensure interaction with the stationary phase is not overextended?
Mm-hmm. So it would depend as well if the peak broadening is occurring on, is it all of the analytes, or is it a select few, or is it just one? And I think what you can have a look at is when we go back to, I don't know if I can go back to it, there's a lot of slides for me to click through, but when we have a look at harnessing the temperature, maybe you can look at adjusting the temperature and making sure that the analyte isn't staying on the column for too long. I know it is tough sometimes, especially if some of the methods are established and you don't want to change them too much. We'll get there eventually. But yeah, I think it's just double checking in your method, what are you able to change? So if there's too much retention, just have a look at what sort of film thickness are you using? Is it maybe too thick? Maybe are you using other columns that maybe they work better with a thinner film thickness? Or is the temperature something that you can change of the oven? So just reassessing those aspects of the method and just double checking what you can and can't change. And you may just need to decrease the temperature or increase the temperature just to try and adjust the retention so it's a bit more suitable for what you're running.
So another question is around internal standards. Do you recommend using internal standards to improve repeatability of the percent RSD on the peak area for the system suitability?
I would definitely recommend using some sort of internal standard, just because if there's any slight variation in your sample, so I'd recommend to try and use that, and just have as many options to test the reproducibility and repeatability, just so you're not going to have any doubt if you just say using one standard. That would be my recommendation.
So a lot of requests for the recording of the webinar. Just so everyone's aware, we will have a recording of the webinar that you can download off of the website. So with that, unfortunately, I think we're out of time. If you did have any questions that we did not get to, we will follow up with you via email. On behalf of MacMod Analytical, I want to make sure that everyone knows that these products are available through MacMod. I want to thank Kirsty for a terrific webinar, really fantastic job, very educational. And thank you all for attending, and we hope to see you all soon on future webinars. If we have scheduled GoToWebinars at this point, we can move them forward. So please stay tuned for the GoToWebinars in the future. And if you have any questions, thank you very much. Goodbye.
Thank you. Thanks very much.